Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. We continue our DSC chapter with part 3. Okay, we proceed with the polymer crystallinity. Okay, we can measure the crystallinity of the polymer by look at the delta HF, which is known as the heat of fusion. So heat of fusion, the unit used is a joule over gram. And if the degree of crystallinity increase, the heat of fusion will also increase. The enthalpy of fusion, also known as the latent heat of fusion, is the change in enthalpy resulting from heating a given quantity of a substance to change its state from a solid to a liquid. So the temperature at which this occurs is melting point. And the energy required to change a gram of a substance from the solid to the liquid state without changing its temperature is commonly called as a heat of fusion. The important percentage of the crystallinity will affect the end-use properties because it is an indication of the heat history during the process. And we have annealing, annealing, which is the heat or metal glass and allow it to cool slowly in order to remove the internal stress and tough it. It is actually the heat treatment that alter the physical and sometimes the chemical properties of the material to increase its ductility and will reduce its hardness, making it more workable. And it involves the heating a material to above its crystallization temperature, maintaining a suitable temperature and cooling it. Okay, for polymer, we prefer to slow cooling of the polymer during the crystallization temperature. As we all know, the slow cooling polymer, okay, if we cool the polymer slowly, okay, so we can achieve the higher crystallinity because the polymer produced is smaller size, okay. And if we choose to cool the polymer by using the fast cooling, we will get higher size of the crystallinity, which is tend to produce lower crystallinity. So slow cooling will produce small crystal, which is better crystallinity, and the fast cooling will produce big size of the crystal, which is will lead to produce a lower crystallinity percentage. How can we measure the percentage of the crystallinity? Okay, the experimental heat of melting, which is delta H of fusion, is measured by integrating the area under the melting heat and is then compared to a reference value, which is delta HF naught, as shown in the graph, which represent the heat of melting of the theoretical 100% crystalline polymer. So this value is given in the table. You don't need to memorize it. It is the fixed value for 100% crystalline polymer, and you just need to use the formula delta HF divided by delta HF naught times with 100. So delta HF here you can measure or figure with that on the graph of DSC divided by the 100% of crystalline polymer. As we can see in this example, you need to calculate the percentage of the crystallinity for LDPE sample. And the delta H value is the delta HF fusion that you need to examine on the graph. So the value is delta H for 100% crystallinity for a DPE bottle is 275. This one is the reference value, which is delta HF naught. And the value given on the graph is 153.81. So by substitute the value by using the formula, you can get 56.3% of the crystallinity of LDPE bottle. Now we look at the crystallization behavior. Okay, the crystallization rates, okay, which is the rate of the crystallization or the polymer become crystal, it will affect the final properties bearing. First, we can see that this curve here is the effect of heating rate on the crystallinity. As I explained in the previous slide, by cooling the polymer so quickly, so the material does not have time to crystallize during the cooling and form a completely amorphous, which is non-crystalline structure. So if we use the fast cooling step, we can get an amorphous polymer, which is the polymer that have a big size of crystal and actually big size of the molecule. And when the polymer is big size of the molecule or crystal, we assume that it has a amorphous structure, which is non-crystalline. So it will the effect of the greater crystal profession at the slow heating rate. So we can produce a small crystal size which is produce highly crystalline polymer. If the crystal size is big, and we assume that it is an amorphous polymer. Okay, now we look at the DSC application. First, we can use DSC for the characteristic temperature of transition determination. Transition temperature, which is in here, it plot as a TMG. It is the TG. TPM is actually melting temperature, and TPC is crystallization temperature. So the DSC curve in the region of a phase transition and the corresponding characteristic temperature, and we can see that the curve is endothermic, which is the arrow is going upward. So TG is going upward, the TM is going upward, and TC is going downward. We can also use DSC for enthalpy determination. So the area of a DSC peak can be used to estimate the enthalpy transition, which is the delta H, which is the area that is inside the curve, okay, and also the below the curve. This one is the factors affecting on the result of DSC measurement. We have sample calibration, sample pen, depend on the types of the sample pen used, depends on the amount of the calibration of your machine done. And for example, the most important effect is the sample mass and also the experiment condition. The way that you set the heating and the cooling rate will affect the DSC curve. And the result interpretation, purge gas, and also the environment condition. The DSC has several advantages such as the wide range of temperature, program heating or cooling rate. It is sensitive, any material may be tested, any form of material may be tested, small amount of material is needed and it does not take much time, and clearness of the result. Some DSC disadvantages, it cannot really control the rate of the experiment, and we can check with thermocouple. It dependent on too many parameters such as in the previous slide. It very sensitive to any changes such as the heating rate and so on. The result depend a lot from the operator. If your operator is highly skilled, so it is the advantages for you to interpret the result because it is depend on its skill. The procedure of standard parameter evaluation is not described precise and has lack of thermodynamic background. If your machine is not calibrated, so it will affect the result as well. DSC used in the quality control, we can use it is very important for you if you work in the quality control um, department, because you need to characterize the thermal characteristic of the polymer on the material, and you need to know the temperature of the transition, the enthalpy of transition, specific heat capacity measurement, delta H, and you can identify the material, the percentage of the crystallinity, how much the purity of the material, and any chemical or physical transition revealing, and also know how stable the material is by observing the temperature such as the Tm, Tg, and also the Tc, and also the degradation temperature and cross-linking. DSC used in quality control for crystallinity estimation. We can know the percentage of the crystallinity by measuring the area below the curve by using the formula given, such as I showed in the previous slide. This way, it shows how to calculate the percentage of the crystallinity as I showed um, just now. Okay, in this example, we can see that the Tm we got here is 167, and the delta Hm, which is the area below the curve, is 173. So according to the result of the 100% crystalline polymer from the reference literature, we got 207 value. So just divided 173 joule over gram with 207 times with 100, and we get the percentage of the crystallinity of PP measured on the graph is 84%, which is highly crystalline polymer. So more likely it is a POM material. For DSC in purity estimation, the DSC curve of a substance at 3 purity level, we can see that there are 3 types of the purity. The first graph is material that is unaltered, a pure material. The melting of a pure material takes place over a narrow range. Okay, this one is the pure material. And the result is sharp melting peak on the DSC curve at a temperature characteristic of this material. The impurities will cause the gradient of the temperature in the sample. As we can see that the peak is shifted, right? And as a result, the melting peak broadens and the melting temperature is shifted. For the characteristic temperature of transition determination, we can assume when the polymer will be degraded. Okay, because we can estimate the degradation temperature of the polymer, which is the rate or the temperature after melting temperature. Okay, polymer are very sensitive to degradation reaction occurring both during the processing and during use. So, dominating degradation process by oxidation, thermal oxidation, and also photo-oxidation. We can observe it by the color change, properties change, and actually we need to prevent the degradation from occurring. And then we can know what um, what we need to do to overcome the degradation to be happen. Okay, for the DSC in oxidation stability estimation, it is the information about the stability of the material from the analysis of decomposition reaction. Okay, one widely used standard test method is the measurement of the oxidation induction time, or OIT. OIT is the difference in stability towards the oxidation between the material. Okay, this measurement also allows thermally, mechanically, or chemically stressed material to be distinguished from fresh material. Please try to do this.